So as a way to consolidate what we have learned so far, I would like to discuss in detail an example about balls and boxes, distribution of balls in boxes. Okay, so we have n boxes, and we draw at random r balls with the idea that every ball can go in every box with the same probability. And well, as we have seen, there are many problems that can be reduced to this example. But what we have seen is also that we can compute the probability that when you draw r balls into n boxes, then all the boxes are filled, so there is no empty boxes. Okay, and we have seen that this is this explicit expression Okay, so this is the probability that after you draw r balls into n boxes, there is no empty box. All boxes contain at least one ball. So, so this is a rather complex expression. So what I would like to do is to use what we have learned so far to understand better this problem and get more explicit results than this. So there are different questions that one can ask. So type of questions are, say, for example, we should see that this probability should be equal to 0 when r is less than n. Okay, it's not at all evident from this expression. And second question we can ask is how much time do I mean, if you think of drawing balls one at a time, you can ask how much time do I need to wait? How many balls do I need to put into this box to fulfill this condition that no box is empty? So this is a problem that can be casted as a waiting time problem. So you would like to understand what is the probability that you have to draw r balls in order to fulfill this condition, and or you would like to compute what is the expected value of t, so to get an idea of typically how many balls you have to draw. In particular, we want to understand this question also for n small. Of course, you can do the calculation, but for n large, it is not at all clear how what the answer to this question is from this formula. Okay, so we want to study the, in particular, the asymptotics. Okay, for number of boxes that goes to infinity. And the last question is, now imagine that I want to generate a random variable. I want to generate a random variable, a waiting time t, which has exactly this distribution. How do I do? How do I sample this distribution here? Okay. So this is the question that we are going to address. So let's start from the first one. And the idea is to take this as a sequence for each n. We take it as a sequence of numbers with r, and we build the generating function. So let's call it Pn of s, and this is the sum of r equal to 0 to infinity of P0 Rn times s to the n, to s to the r. Okay, so when you do this, you multiply this by s to the r, and you sum over r. You see that the sum over r can be done, and it gives you a geometric series. So it's just this times s to the r summed over all r, and this gives you exactly so everything else remains the same. So this part remains the same, but the geometric series, when you resum it, it gives you 1 minus nu divided by n times s. Okay? Okay, so this is the geometric series. It is not yet an easy expression to handle, so we would like to simplify it a little bit more. And so here we use a simple relation that whenever you have something like 1 over q, you can put it at the exponent by introducing an integral. Okay, so there is this identity that we are going to use in order to change this thing. So so if you do this, then let me take the integral before. Then you're going to have the sum over nu from 0 to n minus 1 to the nu, n choose nu, and then you're going to have e to the minus q, which is 1 minus this, 1 minus nu over n to the s times s, everything times t. Now you see that when you have a term which is e to the minus 1 minus s times t, that can go, that does not depend on nu, so it can go out of the sum. 1 minus s times t. And then what remains is e to the minus nu over n times s times t. And this is something, so this is something that is a power of nu. So you can put this and complete, use the binomial expansion and write this as 1 minus e to the minus s times t over nu, over n, sorry, to the power n. Okay, so this is already a somewhat simpler expression, but we can simplify it even more. And in order to do this, we make a change of variable where u is e to the minus s times t divided by n. So essentially du is minus s over n times e to the minus st over n, which is u times dt. So you can change the integral in t into an integral in u from 0 to 1, and then you have a factor n divided by s, which comes from the Jacobian. Then what you have here is essentially u to the power n times 1 minus s over s. And here you have 1 minus u to the power n. Okay, so this is a simpler expression because essentially this expression, this integral, is just a beta function. So the beta function is just defined as the integral from 0, 1 in the u to the a minus 1, 1 minus u to the b minus 1. And it can be the beta function can be expressed in terms of the gamma function as gamma of a times gamma of b divided by gamma of a plus b. Okay, so what you see from this that this integral becomes just n over s times the beta function of n 1 minus s over s and n plus 1. Okay, so what makes our life even simpler is the fact that the beta function satisfies the recursion relation that the beta function of a b plus 1 is equal to b divided by a plus b times the beta function of a and b. And this you just this relation you just deduce it from the fact that gamma of b plus 1 is b times gamma of b, and gamma of a plus b plus 1 is a plus b times gamma of a plus b. Okay, so now you can take this equation and apply it n plus 1 times. So if you apply n plus 1 times, then you will have n plus 1 factors like this one, where a is this and b is reduced by 1 every time. And then you can use the fact that, again, because of this relation, p of a and 0 is equal to 1. Okay? So if you do this, then you get, and you do a little bit of algebra, then you find that this generating function becomes n times s to the n product over k from 1 to n of 1 over n minus k times s. Okay, so this is a somewhat simpler expression, and what is important is that in this expression you find that the generating function starts with a factor which is s to the n. So all the coefficients in this power series with powers s to the r with r less than n are equal to 0. Okay, And so this means that this is true. Okay? So this is the first thing. Then, well, the second thing that we would like to understand is, well, how much time do we have to wait for this condition to be satisfied. So let me rewrite this. As n factorial s to the n product k from 1 to n 1 over n minus k times s. Okay, so okay, very good. So by the way, another sanity check that you could check from this is that, of course, we know that Pn should be n factorial divided by n to the n. And in order to do this, you have to look at this expression and check what will be the coefficient of s to the n in this expression here. And well, of course, the coefficient of s to the n is obtained by taking s equal to 0 in this part. And then you see that you get exactly this expression here. So, okay, so it is always useful to have a way to check your results, and when you can check your results whether they are correct or not, you should do that. Okay. Okay, so now let's go to the question of waiting times. Okay, so we want to define this waiting time as the number of balls that we need to have in order to fill all the boxes. Okay, and we want to define the probability of this waiting time to be equal to R as a probability FR. And now what you can realize is that this probability, so the probability that there are no empty boxes when you put R balls into N boxes, is exactly the probability that T is larger than R. So this is exactly equal to this. Okay? So so this is the, if you want, this is the cumulative distribution. And we have the generating function. So as we have seen, we can get the generating function of this probability distribution if we have the one of the cumulative distribution. In particular, if you build the generating function of this random variable s, which is just the sum over r f of r times s to the r, then it is clear that the, say, P0 of r and plus 1 and n will be equal to P0 of R and n plus f of R. So this tells you that the probability that t is larger than R plus 1 is the probability that t is sorry. The probability that t is larger than R is equal to the probability that that t is equal to R plus the probability that t is larger than R plus 1. Okay? So if you take this equation and multiply by s to the r and sum over r, then you get the expression that this generating function must be equal to 1 minus s times Pn of s, which is 1 minus s times n factorial s to the n product over k 1 over n minus ks. Okay? Okay. So, very good. So now, first thing we can do is to, well, you see this, this sum goes from 1 up to n. When n, k is equal to n, you have just 1 over n times 1 minus s that cancel this and the factor n. So you can write this f of r in a more compact way as n minus 1 factorial times s to the n product k equal 1 to n minus 1 over n minus k times s. Okay? So, very good. Again, a sanity check here is that f of 1 should be equal to 1. This probability should be normalized. Okay, when we set s equal to 1, this is 1, and this is 1, and this product just gives you 1 over n minus 1 factorial, so it cancels with this, so this is okay. Okay? Now, once we have the generating function, we can compute what is the expected value of this waiting time. And in order to do this, we know that this is just given by the first derivative of the generating function computed in s equal 1. Now, because this is a product, I find it easier to write this as f of 1 times the derivative of the logarithm of f of s computed in s equal to 1. So this is an identity because, of course, the derivative of the log of f of s is f prime of s divided by f, and if you multiply by f of s, then this is 1. This is just f prime of s. And it's useful because the logarithm of a product becomes the sum of the logarithms. So essentially, f when I compute it in 1 is 1. So this is the derivative of the log of n minus 1 factorial. This is just a constant plus n times log s plus actually minus a sum from k from 1 to n minus 1 of the log of n minus k times x. Okay, and do this derivative, and then you take it as x equal to 1. And so what do you get? Well, you get n divided by s, but then s is equal to 1, so the derivative of this just gives you an n, and then you get minus the derivative of the logarithm is just is a minus k here, so you get plus k from 1 to n minus 1, you get k divided by n minus k. Okay, so now if you add here n and subtract n, then you can rewrite this as in a simpler form as just 1 plus n times the sum from k equal 1 to n minus 1 from 1 over k. So you see, we can compute the expected value of the waiting time in explicit form. Now this sum of the inverse of the integers is something that if you want to estimate for large n is an asymptotic expression, and actually it goes as the logarithm of n. Because it's just like the integral of 1 over x, which gives you the logarithm of x. And so asymptotically this becomes equal to n log n plus n times gamma plus 3 over 2 plus orders of 1 over n. Where this gamma is Euler constant, and this gamma is 1.621. Oh, sorry, no, this is another constant, so 0.572. Okay, so what you get from this is that essentially this is the expected number of balls that you need to put in the boxes in order to satisfy this condition that all boxes will be empty. And so this tells you that you need to put an order logarithm of n balls in each box. Okay, so the number of balls per box should be order log n. Okay, so so we would like to understand why is this so. And in particular, well, you can do a lot more calculations with the generating functions, but we would like to get some understanding of why do you need these log n balls per box. Okay, so and the question is what is it that makes this formula so complicated? So why is this such a mathematically complicated program. Okay. So in order to look at these two problems, so let me consider this problem when you look just at one box. We look at just one box and we ask what is the probability that there will be a certain number, say, of balls, so let's say B1, Bi is the number of balls in box I. Let's say this depends also on R after R grows. Okay, after you put R balls, you look just at box Bi, and you want to understand what is the probability that this random variable Bi of R is equal to, let's say, K. Now, the problem is simple because this is just a problem for every of Bernoulli trial. So every ball that you draw either goes in box I or it doesn't go in box I. And the probability that it goes into box I is just 1 over n. Okay, it's 1 over the. So this probability is just R choose K times 1 over n to the K, 1 minus 1 over n to the R minus K. Okay? Now we are interested in this probability in the limit when the probability gets very small and the number of trials get very large. So we know that this probability is asymptotically well approximated by a Poisson distribution, which is where essentially the mean is just the number of balls divided by n, the number of balls per box, times e to the minus R divided by n. Okay, so now the problem that we want to ask is so you see, now if you consider the problem, the original problem, which is the problem that Bi of R should be smaller, larger than 0 for all I to 1 to n. So this is our original probability. So what makes life complicated in this problem is that the number of balls that go in each of the boxes is not an independent random variable. Okay, they are independent, and why they are independent? Because the sum of I from 1 to n of the number of balls that go in each box must be equal to R. Okay? So this is what generates all the complication in this problem. Okay? In order to do this, you can you can ask, so what if, say, if we take this approximation where the number of balls in each box is a Poisson distribution, then also this sum will become a random variable, because all of these are random variable. So what type of random variable will it become? Well, so if we take this random variable as being the sum over this Poisson random variable, which have this distribution, then you can get the distribution of R by using the generating function. You know that the E of the expected value of S to the R must be equal to the expected value of S to the BI of R. And if these are all independent, then this must be raised to the power n. And because this is the generating function of Poisson random variable in this approximation, then this is just E to the minus minus 1 minus S times lambda, which is R divided by n. And this should be raised to the power n. Okay? So, this becomes just e to the minus 1 minus s times r. So, if we now interpret R not as the number of balls, but as the expected number of balls, and the true number of balls is a random variable, then you see that we can consider each of the random variable which count the number of balls in each box as a Poisson random variable. And what happens in this approximation when we compute P of, so if we compute the expected value of this probability, where R now is a random variable with a Poisson distribution with mean equal to R. Okay? Then, well, we have to take this expression here and take the expected value on the Poisson distribution. So this is sum mu from 0 to infinity minus 1 to the nu n choose nu, and then you have the expected value of this on the Poisson distribution. So so now I'm calling R the expected value of capital R. So I take the sum on k from 0 to infinity. The probability, which is R to the k over k factorial e to the minus R. This is the probability. And then I have 1 minus nu over n to the R. Okay, so as you can see, this sum just gives me the exponential. This is a power series of the exponential, and what I get is as a very, so this object is just e to the minus r times e to the r, what's it, 1 minus nu over n. Okay, and you see that r and r cancelled, so this is just e to the minus nu times r over n. Okay, all of this is e to the minus nu over n. So, and then you see that I can also perform this sum here, because it's just the binomial expansion of this. So, and what I get is a very simple expression. This is just e to the minus r over n to the power n. So this is a very simple interpretation, because you see now this is the probability. So this is the probability that one of the box is empty, that k is equal to 0. So this is the probability, 1 minus this probability is the probability that box I is not empty. And because these are all independent, I just have to raise it to the power n to get the probability that all boxes are not empty, that they are filled by some particle. Okay? So you see that when I replace R by a Poisson random variable, then this problem simplifies considerably. And now you can ask how big should R be in order for this to be order of 1? And so in order to do this, so this object, in order for this to be of order of 1, should be of order 1 over n. Okay? So e to the minus r over n should be of order n. Of order 1 over n. So n times this should be of order 1. So this tells you that R should be of order n times log n. Okay? Okay, so this answers the question we have posed. So why is it that this time is of order is of order n log n? But now we can also estimate the probability distribution in this limit. So what we have learned is that so the expected value of t is n log n plus n times gamma plus other smaller things. So these are the leading behaviors. So it makes sense if we want to understand what is the asymptotic distribution of t, to write t as in terms of a random variable which is x, to write t in this form and to ask what is the distribution of x. Okay, so essentially, if you take this expression, this would be the expression is the probability that t is larger than r. Okay. So if you compute then the probability that t is larger or equal than n times x plus log n, then this is given by 1 minus e to the minus x minus log n to the n. And you see that this minus log n just gives me 1 minus e to the minus x to the n, to the power n. And this for n large is very well approximated by e to the minus x. Okay, so this tells you that if you write, if you make this change of value, if you call this variable t as n times a new random variable x plus log n, then this random variable has a probability distribution a cumulative probability distribution. So the probability that x is larger than this is equal to the probability that t is larger than this, and this is e to the minus x. And so this tells you that the PDF of this distribution is just what I get by taking a derivative of this, and it's given by e to the minus x minus e to the minus x. And this is quite interesting because this probability distribution, we will encounter this probability distribution, and it's called the Gamble distribution. And we will encounter when we deal with problems that have to do with computing the distribution of a random variable z, which is the maximum of x random variables, is the maximum of n random variables. And what we will see is that a large class of when xi are independent and identically distributed random variables with a distribution which is in a broad class, then the random variable which is the maximum, describe the maximum of these random variables when n is large, is described by this distribution. So this is not accidental, okay? This is not accidental, and if you think about it, well, you can realize that you can define a time ti, a waiting time ti, which is the time to, so essentially is the time to have at least one particle in box I. Okay, it's the number of balls that you have to draw in order to have at least one ball in box I. And then if you define this random variable for each box, then it is clear that the time you have to wait for all the boxes to have at least one random variable is the maximum of these random variables. Okay? So the fact that you get the Gamble distribution in this case, it is not at all a coincidence. Okay, so essentially we have more or less understood what is the asymptotic distribution of t, And now let us come to the last point, which is how do we do if we want to sample? How can we use what we have learned if we want to sample this distribution? Okay, if we want to draw at random a waiting time that has this distribution, and so to a large extent you can say that you have understood a problem when you can really do calculation, when you can really draw random variables concretely from this from a given distribution. Okay. So so the question we address now is how would you make a computer program that generates these random variables? Okay, so this random variable t. Okay. Now, I remind you, so the problem is that you have n boxes, and let's imagine that n is large, and then you want to put balls into these boxes, and you want to find how many boxes, how many balls you have to draw in order to fill all the boxes. Okay. So one simple strategy is to say, well, t is at least larger than n. So let me start by drawing n balls. Okay. So in this case, let's draw 9 balls. Okay, so then another one. Okay, so after you draw n balls, then you count how many boxes are empty. So let's say n0 boxes remain empty. In this case, n0 would be equal to 3. And then you can proceed in the following way. So you can ask yourself, when I draw one more ball, what is the probability? So it can fall in the already occupied boxes or in the empty boxes. So the probability that the new ball goes into an empty box is just n0 divided by n. Okay? And I can ask myself, how much time do I have to wait for the next ball to fall in an empty box? And this is again a waiting time problem. So the probability that I have to wait a number of balls, let me call it this t of n0, this is the probability that I have to wait k draws is a geometric distribution. Because if I get a ball in an empty box at after k rows, then it must be that k minus 1 rows went into already occupied boxes, and this is the probability. And then one ball went in the empty box, in one of the empty boxes. Okay, so then what you can do is you start from t equal to n, and a certain, and then you fill these boxes in your computer n0. And then at the first step, you draw a number from this distribution. Okay, and this is rather easy. And then you increase your t by k, because you have added k more balls. And at the same time, you will have that n0 goes to n0 minus 1. Okay? And then you see, this tells you that you will have to draw, say, k more balls in order to fill one more boxes. And then you are left with 2 empty boxes. And you continue until you fill all the boxes. In this way, at the end, you will have your t, which is t plus the different random variables that you have drawn for different values of n0 in this process. And so in this way you can compute this waiting time. You can sample this waiting time. Okay, now how can we do it a little bit more, can we be a little bit more clever than this, using what we have studied so far? So the idea is the following. So we have said that if the number of balls is a Poisson distribution, then the problem gets a lot more simple. Okay, so in order to use this insight for sampling this distribution, well, what we can do is the following. So we fix a value of rho, which is essentially the expected value of balls would be the expected value of balls into boxes. And then we draw a random variable R, which is a Poisson distribution. Let me write it in this way, with mean n times rho. Okay, then we draw these many balls. When we draw these many balls into boxes, we know that the probability that box I is empty will be equal to 1 minus e to the minus, so the probability that box I will be empty is e to the minus rho. So, and we know that because this R is a Poisson distribution, these events are all independent. So we can compute directly the probability that n box, what is the probability that n0 boxes will be empty? And this is just given by the binomial distribution, because every box is empty with this probability. So the probability is just given by this. Okay? So you see, you can start drawing this R, and then you can draw an N0. These are just draw two random numbers, and essentially this reduces your problem. When you do this, your waiting time goes into waiting times plus R, and your N goes into N minus N0. Okay? And so you can repeat this step by replacing N by N0. And then you will do another random variable, Poisson random variable, which is Poisson will mean N0 times rho. And you will compute another N0 prime. And so on, and you do this until you hit a value of N0 which is equal to 0. And then you stop, and when you sum all the random variables that you have drawn in this step, you will get a sample of T from the correct distribution of this waiting time. Okay, so the idea of this lecture was to show you how we can use practically what we have used, what we have studied so far, in order to understand in depth a problem that at first sight looks rather complicated. To make calculation on it, also to understand where the complication arises, and to use this understanding in order also to practically do calculations.